The next approach we'll work on is something often known as quick union. So I'm going to summarize the approaches we've had so far. Approach 0 was, let's represent things as boxes and lines and somehow keep track of each individual line, but we ended up not getting anywhere with that, and I didn't even tell you what those Java instance variables might look like. This is way too complicated. There was the list of sets approach, where we have a list of sets of integers, and there was the quick find approach, where we represent the connected components as a list of integers, where each value corresponds to the ID of the connected component for that item. So as we just saw, quick find has the bad feature that connect is slow. We have to combine a bunch of items in order to connect them up. Right? So if we want to actually change the set membership, we have to change many values, all the red values to blue, for example, in order to combine these sets. So in this next approach, called quick union, we're still going to represent things as connected components, and we're still going to be representing connected components as a list of integers, so we're still going to keep the same instance variable. However, we're going to set up our values in this array so that connect is fast. Okay, so that's kind of cool, right? So now rather than changing the data structure, what we're going to do is change the numbers we store in the data structure to represent set membership. And so now a very hard question for you. How could we change our set representation so that combining two sets into their union requires changing but one value? So here I'm showing you the quick find approach where all of these values need to change. Now I want you to come up with an approach where we only need to change one value. Pause the video. This is a pretty fun challenge, I think, and see where you can get with it. All right. So I would have you give me an answer, but I don't know you. You're not here in person. So I'm just going to give you an answer. So the usual trick, the only way I know of to do this, is let's assign each item a parent instead of an ID. Okay? So what I mean by that is instead of saying 2, you belong to set 4, you'll say 2, you belong to item 1, and 1, you belong to item 0, and 0, you belong to nobody. And we'll use a negative value here to represent the root of one of these sets. Likewise, 5, it has a parent of 3, and 3's parent is itself, and 6 has just its own self as a parent, right? So it is a root. So this approach, kind of interestingly, we're moving actually a little bit back towards approach 0. It's not quite the same thing, but it's close. Okay. Now this approach, it seems pretty innocuous, right? It's like, okay, cool, different way of doing things. But it turns out that this is the foundation of what a real state-of-the-art disjoint sets operation looks like. And even more interestingly, it unlocks a gigantic area of CS theory that is just really interesting. There's all this cool math involving inverse Ackermann functions, and I'm not going to talk about it in this lecture, but there's a lot of cool theory that this opens up. Okay, so let's think a little bit more carefully about how this would actually be useful for implementing disjoint sets. So what I'd like you to do to test your own understanding is take this example here that we just saw and try to call connect 5, 2. So if we do 5, 2, what changes? And I have a hint here that if you're not quite sure where to start, you should say, why can't I just set this value to 2? So give this a shot, and then I'll answer it in a moment. Okay, so if we try and connect these, I would, again, take your answer and go through it, but instead I'll just spoil it for you, since I can't get your answer. So what we want to do is we want to find the root of 5, okay? Because one of the key things here is that if we, well, actually, I'll show you what's wrong with the example here. If we just set ID of 5 to 2, if we do this, then we would be connecting 5 below here and orphaning 3 to itself. This is not correct. So instead, what we need to do is tie 3 to be below, let's say, 0. So I can find the root of 5. That is, climb the tree, find 3, can find the root of 2, find 0, and then set this 3, which is the root of 5, to be below 0. So in particular, well, actually, I have an animation already ready set up to go. So I want to change this value here. 3 should no longer be a root, but it should be a subservient item of 0. So that's one approach. And you could also, by the way, have done this and hung 3 below 2, but I like this approach better because the tree is less tall, and we'll return to that idea in a bit. Okay, so that's one way we can implement connect. Now, this approach, there are some potential performance issues. Okay, so you want to, well, I guess the question for you, why might this be a problem? Where can we run into trouble here? So connect, it seemed fast in the sense that I just had to change one value. But what's not great about this? Well, what's not great about it is that the tree can actually get really tall. Finding the root of an item can become expensive if the tree is very long. So here's a question to really see if that makes sense, is let's say that we always connect the first item's tree below the second item's tree. In that case, parentheses failure. In that case, if we did, for example, connect 4, 3, connect 3, 2, connect 2, 1, and connect 1, 0, we would end up with this tree right here. So what I'd like you to do now is tell me what would be the worst case runtime for the connect and is connected operations, keeping in mind that you need to be able to call root in order to answer either of these questions. So I'll pause again maybe, and I'll answer it. Okay, so it turns out the worst case runtimes are both theta n, and we have to fix that parentheses. Or, did I say parentheses earlier? Apostrophe. Geez. Anyway, so we had to fix that apostrophe, and why the answer is theta n? It is because that when we try and connect two items, let's say 4 and 3, then I need to find the root of, if I want to do R4 and 3 connected, I have to find the root, which could take as bad as n time, and then I have to find the root of 3, which takes n minus 1 time, so also theta n, and so the is connected operation is theta n. Same deal with connect. In the worst case, half the items are in one long tree, the other half of the items are in another long tree, and to connect them, you have to find the root of both. So, in case you're wondering what an implementation might look like, I'm not going to show it, I'm not going to talk about it in detail, but this is what quick union would roughly look like, and you may find it helpful to look at this code whenever you're working on the lab. And here I'll note that I'm using the word find to be consistent with the optional textbook for this course. It's the same thing as the root idea we had before. Find finds the root. All right. Now the issue we face here, what we just saw with that runtime problem, is that for n items, the worst case runtime of find is theta n, and since both is connected and connect rely on find, they also have worst case runtimes of theta n. Okay. So here with quick union, we have a constructor that's still theta n. The connect and is connected operations are big O of n, and that's because I've only done a worst case analysis, and I've showed that in the worst case they're theta n. And so I'm just going to use big O here. And the defect here is that the trees can get too tall. So whereas quick find had the problem that connecting was theta n time, with quick union, well, I mean, yes, union is fast as long as you can easily find the root. So the operation can actually be very fast, but if the tree is actually tall, then the connect and is connected operations will be bad. So if the tree is long or imbalanced, then we'd run into trouble. And so the observation I'll make to motivate the next video is that things would be fine if we just somehow kept our tree balanced. We didn't let it get really long. So we'll be discussing that more in the next video. And so see you on that one.